Welcome to a new tutorial. In this case, we're going to talk about the canonical new Keynesian DSGE model, which is often called the three equations model. My name is Juan D'Amico, I'm an economist, and I teach time series analysis and applied econometrics. So if that is a topic that interests you, please feel free to subscribe to my channel to get a notification anytime I submit new content. Now, for this tutorial, it's going to be split into two parts. The first part, we're going to do the theoretical aspect of the model. We're going to take a look at the different equations that interact in the model. And in the second part, is going to be premium access content, where I'm going to be showing you how to estimate, calibrate the model. And also, I'm going to show you how to produce out-of-sample forecast, impulse response functions, and we're going to do some scenario analysis. By scenario analysis, we're going to be modifying some parameters in the model, and we're going to see what are the implications for the model to change the value of those parameters. So let's begin. As an introduction, the standard approach in monetary policies nowadays is to incorporate nominal wage or price rigidity into DSGE models. DSGE models that incorporate nominal frictions are labeled as new Keynesian models. In the past, we have seen real business cycle models, which are models that don't incorporate frictions. DSGE models which incorporate frictions then are going to be labeled as new Keynesian. In new Keynesian models, of course, aggregate demand is going to play a key role in determining output in the short run. There is a presumption that fluctuations in the short run should be dampened by counter-cyclical monetary or fiscal policy. Let's see an overview of the model. We're going to use a model commonly seen in graduate courses. In this case, we will use Walsh textbook called Monetary Theory and Policy, in particular Chapter 8. Now, this model combines a mu model, which is money in the utility function, with monopolistically competitive goods markets and price stickiness. Endogenous variations in capital stock in this model are ignored. Why? Well, because as per McCallum and Nelson, for the US, there is little relationship between capital stock and output fluctuations at business cycle frequencies. This is in the short run. In this model, there's going to be a continuum of differentiated goods produced by monopolistically competitive firms. Now, these firms are going to face constraint to adjust prices, which is what we call the nominal rigidities. For simplicity in this model, wages are going to be flexible. Now, this is very important because the real business cycle models, prices were flexible. There were no rigidities in these models, and in RBC models, they were able to adjust prices. Now, in this model, with stickiness, the firms are going to face constraints when they need to modify their prices. Now, lastly, monetary policy is represented by a monetary rule. Commonly, banks endogenously determine the quantity of money to achieve the desired nominal interest rate. Let's begin talking about the IS curve. Now, the mathematical solution for the derivation of the model is included in the PDF. So for simplicity, in this tutorial, we're just going to talk about the parameters, the equations, and the implications for monetary policy. So this equation we are seeing here then represents the IS curve and is derived from the Euler equation based on the problem of the households. So this equation is going to represent the demand side of the economy. Now, what is it saying, this equation? Well, this curve is telling us that the current output gap, and we understand the output gap as the difference between the potential output and the current output. So that output gap is going to be explained by the expectations about the output gap in the future. This is in the next period, and it's going to be negatively affected by the interest rate. The RT is the nominal interest, and here the expected inflation. So when we subtract the nominal interest with the expected inflation, we get the real interest rate. Now, the intensity to which the real interest will affect current output is going to be amplified or diminished by sigma, which is the intertemporal elasticity of substitution. And here we have that. So the current output gap will depend the expected output gap in the future minus, it's negatively affected by the interest rate, which is either amplified or diminished by the intertemporal elasticity of substitution. This is how consumers are modifying their patterns of consumption based on changes in the interest rate. Now, if they are very flexible, then that means that the interest rate will have more effect. And if your consumers don't have these patterns of modifying their consumption patterns, then the effect is not going to be as strong. Now, higher values of sigma then means that consumers are less willing to adjust consumption patterns to changes in the interest rate. So the higher this value gets, sigma, the lower will be the effect of the rate. Now, the lower the sigma, if we are dividing 1 by a small number, this term is going to get very big, which means that the interest rate then is going to have a big effect on the current output gap, right? That's why it's subtracting here. Now, this move represents a demand shock and follows an AR1 process. A demand shock can be, for example, maybe the consumers now have more disposable income, maybe they have changes in the consumption patterns. There can be many external things that can influence the way that consumers react. So all those things are going to be incorporated into that shock. Now let's see what happens if we modify the values of sigma. So in this graph, which I'm going to show you how to create a graph like this one in the second tutorial, you can see what is the response of the output gap to a change in demand. We have the blue line is showing the baseline scenario, which has a sigma equal to 0.8, and the red line has the counterfactual scenario with a sigma of 0.3. So we are decreasing the value of sigma. Remember that what I mentioned in the previous slide is that if the sigma gets smaller, then the effect of the interest rate on the current output gap will be bigger. So that's why we're seeing that the current output gap is diminishing. You can see that with smaller values of sigma, the current output gap diminishes. Why? Because the effect of the interest rate is going to be bigger. So as a summary, I wrote here the analysis that a smaller sigma magnifies the impact of the real interest rate on the current output gap, and you can see that then the gap gets smaller. Let's now discuss the second equation, that is the Phillips curve equation. This equation we're seeing here represents the Phillips curve, and we are going to derive this equation from the optimal pricing decision of individual firms. The new Keynesian Phillips curve represents the supply side. Remember, the IS curve represented demand side, Phillips curve, supply side. The Phillips curve states that the current inflation is going to depend on expectations about future inflation, and is also positively impacted by variations in the output gap. This Kappa captures the sensitivity of inflation to changes in output. It's going to represent the degree of price stickiness. So inflation then, as a summary, is going to depend on what are the expectations that agents have about the inflation in the future, and changes in the output gap, all right, are going to put pressure on prices. When the economy expands, we can see with this plus sign that is positively affecting the inflation. Now, let's analyze a bit this kappa value. Higher values of kappa imply a stronger response of prices to changes in the output gap. As you can imagine, the higher the value of kappa, if this value gets higher, then the impact of the output gap is going to be higher on inflation. So in this scenario, prices adjust more rapidly, implying low price stickiness. So let me put this in other words. When prices are not sticky at all, this is that there is low price stickiness, then prices are going to adjust quickly. They are going to modify quickly. So the higher, yes, the faster that the prices adjust, then the faster that is going to put pressure on inflation. Now here we have a supply shock and is going to follow an AR1 process. Let's discuss a bit more the parameter kappa. The parameter kappa is a friction that comes from the Calvo pricing model. Now, the Calvo pricing model is the way that we are going to be modifying the firm side to incorporate the friction of price stickiness. And remember, we have mentioned that price stickiness refers to the ability of firms to be able to modify their prices. Now, this parameter is often interpreted as the impact of real marginal cost on inflation because changes in the output gap can influence firms' marginal costs, which in turn affect their pricing decisions and ultimately inflation. Putting this in other words, when there is changes in the output gap, let's say that the economy expands, that's going to put pressure on prices, right? So in turn, the marginal costs of firms is going to change. So if marginal costs change, then the firms are going to adjust their prices to incorporate those changes. Now, all this is going to ultimately be affecting prices. Now, what is this omega? Well, we call omega a random fraction of firms that in a given period do not adjust their prices. So the Calvo pricing model is a dynamic model. We have to think about this as turns where firms are adjusting their prices. Maybe in the first turn, maybe in the first scenario, the firms do not modify their prices, but maybe in the second stage, they will be modifying their prices. Now, what this is introducing into the model, like I mentioned before, in the RBC model, in the real business cycle model, the firms, all of them, had the ability to modify their prices immediately. But now in this model, with the Calvo pricing model, we are just allowing a portion of the firms to be able to modify their prices, but another portion cannot. And this is what is adding price stickiness. The fact that there are being changes in the output, but some firms are not being able to modify their prices. So because they are not able to modify their prices, it's that prices don't change, right? And we don't see then too much pressure on inflation, too much pressure on prices. So if more firms cannot adjust their prices, prices become stickier. The value of kappa is going to be small. Let me go back to the previous slide. And this value is going to become small. If this value becomes small, it means that the current inflation will probably be mainly explained by whatever we are thinking about inflation in the future. But since kappa is very small, then the impact of the output gap is not going to be big on prices. Now, what are the rest of these variables? Beta represents how much weight firms give to expected future profits. Higher expected future profits, smaller is going to be the value of kappa. So higher values of kappa imply a stronger response of prices to changes in the output gap, which is what I just mentioned. And in this scenario, prices adjust rapidly, implying low price stickiness. So, Let's review this again. When the value of kappa is high, that means that price stickiness is low. And now, when the value of kappa is small, price stickiness is high. We can modify the value of kappa and see what happens. We can see what is the response of prices when there is a demand shock. This is when the output gap, for example, expands. What happens if kappa is 0.1 and what happens if kappa is 0.8? Now, the baseline is the blue line, and we can see that with a small value of kappa, this is when the prices are sticky, we can see that the impact on prices is not very big. Now, if the kappa is big, is 0.8, this means that the prices are not sticky. So look how inflation now increases when the output gap expands. You can see then that kappa, the price stickiness, does play a crucial role in seeing how changes in the output gap are going to have pressure on prices. Let's discuss now the last equation in this model, which is the Taylor rule. So let's recall the first equation was the IS curve. It was the demand side of the economy. The second equation was the Phillips curve, which was the supply side of the economy. And the last equation then is the Taylor rule, which is going to represent the monetary policy. Now, central banks implement monetary policy through control of the nominal interest rate. In this setup, the central bank responds to expected inflation, and also they are responding to deviations in the expected output gap. So this phi is how much weight the central bank is giving to prices, and this also represents the phi 2 represents how much importance the central banks provides to changes in the output gap. So let's put this in simple words. Anytime that the inflation increases or decreases, the central bank can react to those changes in prices, and anytime that the output gap changes, the central bank can also react. Now, the Taylor rule was found to be 1.5 for phi 1. I'm sorry about this. I'm going to modify now the slides. This should be phi 1. And here goes phi 2, and this value was found to be 0.5. Now, Taylor estimated these numbers based on the Fed rate during the Greenspan period. Of course, these are all values that we can estimate in our models. The idea is that we estimate how the central bank is responding to changes in inflation and to changes in the output gap. But to find a model solution, what is found is that the first value has to be certainly bigger than 1. Otherwise, you are not going to be able to find a solution in this model. So in this setup, then the central bank reacts more than proportionally to changes in inflation, and it responds moderately to changes in output gap. This is what we can see with the values. We can see that the way the central bank responds to inflation is more than proportional than the way that it responds to changes in the output gap. Now, these now are unexpected changes in the policy rate. Let's discuss now what is the transmission mechanism. This is how changes then in the nominal rate are going to be having an impact on the IS curve and the Phillips curve. So the impact of monetary policy on the output and inflation operates through changes in the nominal interest rate by the policymaker. The assumptions of money neutrality only hold in the long run in the model, but we are allowing to have real effects in the short run. We can see how changes in R, when we change R, is going to modify the output gap, right? So consequently, the output gap is going to put pressure in inflation, depicted by the Phillips curve equation. So when the central bank changes R, we can see right away that is going to have an impact on the IS curve. And the IS curve is going to have an impact on the pressure that it puts on prices through the Phillips curve. Consequently then, the central bank is going to respond by changing the rate. So anytime that there is, for example, a shock in demand, is going to put pressure on prices, and consequently, the central bank is going to be modifying the interest rate. Now, what is next? Well, in the next section, we're going to be looking at a hands-on example. We're going to be using inflation, growth rate, and the Fed rate for the US. We are going to be producing the impulse response functions and doing the analysis. And we're going to be producing some out-of-sample forecasts. So if this is something that interests you, please click the link in the description. I hope you found this theoretical aspect useful, and I hope to see you in the second part where we are going to discuss how to estimate all this in Stata. Thank you very much.